Chapter 4 gives us some of the modern history of astronomy. Chapter 3 ends with ancient astronomy. Chapter 4 starts with ancient astronomy. How do we figure things out? Last lecture introduced the idea of how we went from the ancient times up to more modern times. Again, in Europe, they went backwards. They kind of forgot about a lot of the work that the Greeks did. The later Greeks went all the way back to Aristotle. And as they did so, they kind of lost track of things. The Arabs actually kept the knowledge alive in the Almagest, and so the Almagest was copied and distributed and was known in the Arab world as a way of calculating the equations, and there are ways of calculating very, very high precision where things were going to be in the sky. And Europeans eventually rediscovered the Almagest and Ptolemy's work and went past Aristotle. The Arabs had occupied and controlled Spain for a long time, and when the Europeans moved back in, they found some of the works that the Arabs left. Well, with that this was also close to about the time of a new Renaissance age in which people were studying how things worked rather than just accepting this is the way it is. It was like, well, let's explain this. This was the era of natural history in which biologists were studying plants and animals and trying to categorize different kinds of species of things, and a time of exploration, and many, many wonderful things were going on in terms of learning how the natural world works. Well, astronomy was no different from all that. It was part of this whole study. Now, one of the things we had talked about before was the problem with the calendar. And that was that they had realized the calendar did not really track Easter the way it should. And so the Catholic Church set about trying to figure out a way of keeping track of time better. So all over Europe, they had cathedrals and churches that were built aligned with the heavens to monitor things. There was a lay worker of the church by the name of Nicholas Copernicus. And Copernicus was one of these people that was collecting the data and analyzing it, trying to figure out why the calendar wasn't working right. Well, he wasn't just looking at the calendar, he was also looking at many, many other things in the sky. And he started to realize the basic understanding they had was not right. Aristotle definitely was not explaining the motions of the heavens. Clearly the Almagest was doing better with that, but then the whole epicycle thing didn't make any sense. And so he was trying to figure out what was going on. And so after extensive study, he decides there's a better way of explaining retrograde motion. And he decides that the geocentric model that had been in use in Europe, pretty much since Aristotle and before, that and the ancient Greeks, that was not really an accurate way of doing it. And so he proposed that, in fact, the sun was the center of the solar system, that the planets, including Earth, all went around the sun, and the moon went around the Earth, and the stars were just way out here fixed in space beyond everything. And this was his idea of the universe. Basically, the entire universe centered on the sun. He had no idea what stars were, so this was the idea they came up with. So this was a heliocentric model. And now, remember, the Aristarchus had proposed a heliocentric model in ancient times, but was discounted on the idea that as Earth moved around the sun, as it moved, the vantage point to the stars didn't change. Copernicus went one step further, though, and said the stars, though, are so far out that Earth's motion around the sun makes that motion in the sky, that shift, too small to measure with the naked eye. And in fact, that's exactly correct. That shift is measurable today, but with modern instruments. So he said that what happens is the planets closer to the sun are going to go around faster than the planets further out. And so they're both moving, and so if you're looking from Earth to the planet, it looks like it's moving in the sky, but when Earth is close to the planet, we're going faster and we're passing it. As we pass it, the planet looks like it's going backwards in the sky. Once we're on past, then we see the forward motion of the planet again. So the planet would look like it's going forward, backwards, and forward in the sky. Retrograde motion. So this explains retrograde motion without having to do those silly little epicycle things, something going around nothing. Now the problem with something going around nothing was that didn't even work. So it had to have something going around nothing, going around something, going around nothing, going around nothing, going around nothing, going around nothing. So you had epicycles around epicycles around epicycles around epicycles around epicycles. And so that was just really, really complicated. And so here's kind of an animation showing how this would work with planets moving around all in one direction. And so just the inner planets going faster than the outer planets. And so this seemed to make a lot of sense. The Copernican model is an example in science of what we call Okemos Razor. Okemos Razor says, okay, so you've got several different ways of explaining something. The simplest way of explaining it is normally the right way. So what's simpler? Having all the planets going around in the sun in the same direction, one passing the other and making the outer one look like it's moving backwards, or having a planet going around a bit of nothing that's going around a bit of nothing, which is going around a bit of nothing, which is going around a bit of nothing. I mean, which of those is the simpler idea? Well, obviously, everything going around the sun and passing one another is a simpler idea. And so that's Okemos Razor says that simple idea is more likely to be the correct idea. Now, that doesn't always work, but it actually amazingly works most of the time. That the simple idea is, the simple explanation is often the simpler one. And so the Copernican model, this idea that he had of the solar system seems to be the better one. Okay, it makes life easier also because it's real simple to calculate motion around a circle. That's something that we do very easily in physics. Teach the first year physics students how to do this. First semester physics students, this is pretty straightforward stuff. Copernicus' work also changed a philosophy of science. Okay, something in philosophy they called the Copernican principle, and that is that up until this point, and again, Aristarchus actually had a heliocentric model, but it was largely discounted. But most scientists, thought that the Earth was the center and everything goes around the Earth. Copernicus says the sun's the center and everything goes around the sun, including the Earth. Well, the moon goes around the Earth, but pretty much everything else goes around the sun. And so we're not the center of it all. And so this sort of changes a philosophy. If you think you're the center of everything, you behave a certain way. If you think you're not the center of everything, you behave a little bit different way. So people who believe themselves the center of all things, they want to be the center of attention, they have a certain attitude towards other people, whereas other people who don't think of themselves as the center of everything and everything going around them, tend to have yet a different attitude towards their neighbors. And so the Copernican principle changes even how science thinks. If we're not the center of everything, maybe it's not all done just for our benefit. So we need to figure out, what's going on out there, how's it working? And so, again, it changes a philosophy of science, makes computing things easier. His work is so important that several stamps have been issued in his honor. In fact, his image has been on some banknotes, money. I have a banknote from Switzerland that has Copernicus on it, and from a bunch of years ago. And this is actually a stamp. I collect stamps, and so this is a stamp from the United States that has Copernicus on it, issued back in 1973. Now, Copernicus's ideas were great, but they were not perfect. He made one major error. He assumed all the planets go around the sun in perfectly circular orbits. because that just seemed to make sense to him. The heavens are perfect. Everybody since ancient times assumed circle is a perfect shape, and so he assumed perfectly circular orbits. Well, that did not exactly match precisely the observations. They were slightly off. So what he did was, in order to make the math work, he assumed the planet did go around one epicycle, but it took one exact orbit to go around the epicycle. So on one side of the orbit, it's a little further out. On the other side of the orbit, it's a little further in. Okay, so he did assume that perfectly circular orbits with one epicycle. And so that was a mistake that he made. But if you look at kind of what it does to the orbit, it does make the orbit look kind of elliptical, which is the correct shape. So he accidentally kind of stepped into that. But this was the idea that he came up with, and so this was the Copernican model. I want to mention something else, though. And that is that science is not really just done by scientists completely independently from society. Scientists are part of society, and society does interact with scientists. So when scientists do something, they have to be part of what's going on around them. That's why sometimes you have issues that you have good science, but they come up with an unpopular discovery and they are ostracized. Copernicus was no exception here. He came with an idea that things were going around the sun. Well, this was at a time in Europe in which the Catholic Church had a huge temporal power, and was really a lot of the governments were deferring to the church. And so the Catholic Church was teaching Aristotle's views, and was teaching that the earth was the center of the universe. Now, this was about the time that some people were challenging some of the teachings of the church in religious matters, and so the church kind of like came down and said, oh, wait, anything that challenges anything we say is potentially heresy, whether it's something in the Bible or something that's not. And so this was not something in the Bible, though the Bible did sort of, make it sound like, the earth is the center of things. But when he said this, he wrote it in a very detailed fashion, primarily for mathematicians, and published it. He spent the next number of years working through his model in great mathematical detail, explaining all the details. And then he died, but this was about the time the Protestant Reformation was getting started, and the publisher was afraid of being charged with heresy by saying that the sun was the center of the universe instead of the earth. So when they published his work, they had a preface put into it that Copernicus, of course he was already dead, so he didn't know about it, said that everything that follows is just a mathematical model, but not real. And so they published it, and they were so afraid that he'd be charged with heresy even after death, because they actually did that to people in those days, that they buried him in secret. Interestingly enough, in 2005, they knew that he was buried somewhere near the Frombork Cathedral, and as they were renovating the cathedral, they found a grave underneath the floor that had been partially collapsed, and it belonged to a 70-year-old man. Well, Copernicus was 70 years old when he died. They actually had one of his descendants donate a DNA sample which matched some DNA found in the hair in the corpse, and they realized that they'd found Copernicus. And so they reburied him in 2010, and they also did a forensic reconstruction of him so that we now know what he looked like at his death. And so the new burial site, there's the marker right there for it. And so there we have Copernicus, and he's been found and reburied. And now he actually has a proper tombstone. Okay, and like I said, in 2008, they actually figured out what he really looked like.